What's going on, everyone? You're back with Jono for another quick math lesson. Today we're going to have a look at trigonometry, but not as you've seen it before. We're moving from our right angle triangles, our SOHCAHTOA and all of those things, and we're moving into this thing called the unit circle. This is a big leap, but students usually really freak out just because we're going from triangles to circles, and they don't look the same. But I guarantee you that the maths you've learnt in the last couple of weeks is easily going to be enough for you to nail this topic. This first lesson is a little bit theoretical. There's quite a lot of notes, a bit of explanation, so I really highly recommend just watching this, copying down the notes if you get a second afterwards, and then we're going to start applying some of these theories into exam style questions in later videos. So this is what the unit circle looks like. We've got a Cartesian plane, we're on an X and Y, and we have a circle that's got a radius of 1, and that's actually really important. The fundamental idea of the unit circle is that anywhere on the circumference on the circle, we need to be able to work out the point. And we can do this using our trigonomic functions. So I'm going to find a point xy somewhere in this positive quadrant. So where x is positive and y is positive. It's really important to note that I could have picked any single point on this circle, but I'm choosing this point just kind of randomly. So if I've got a point here, it must have some coordinate x, y. We know that from year 7, so that's not too difficult. Where trig comes into play is that if I draw a line from my point directly into the origin of this circle, I know exactly that that distance must be 1, because that is the radius. So while we've got this radius of 1, the other thing that defines where this point x and y is how far up it is from our horizontal line. So there's actually an angle of elevation that's come into this. So if I draw a line from here all the way up to there, the size of that angle will obviously change where the x and y point is that I've selected. So this is starting to look like a right angle triangle. I've got a diagonal line that's got a 1, and I've got some angle of interest. And the x and y coordinates really just tell me how far across is my point and how far up is my point. And both of these are perpendicular lines, so it's going to create a right angle if I draw them in. So if I want to find out how high up this point is, or this line here, I can now see that I could find this unknown point y pretty easily. If I have an angle of interest and the hypotenuse, I can see that that y is the opposite side of my angle of interest with a hypotenuse. So the formula for this is incredibly easy. It's just sine of that angle is equal to y over 1. Y over 1 is equal to y. So sine of the angle is equal to the coordinate y. So what's really important is instead of talking about a ratio, we've been talking about how sine theta is equal to opposite over hypotenuse. Now we're saying that sine theta is just a distance. In this example, it is just a distance y. We can find the sine length just using our trig. So now if I wanted to do the same thing to find the x value, or how far across the x-axis I've gone, I can do the exact same thing. If I fill that line in there, I can see that I've got a hypotenuse, an angle of interest, and the adjacent side. So that x distance is just cos theta is equal to x over 1, which is just equal to x. So again, both of these ratios that we've been talking about with trig are now supplemented into actual lengths that can tell us heaps of information off this Cartesian plane. So this means that another way to define that point x, y at the very start, instead of having two random variables, x and y, if I know the angle of interest that's made between the x-axis and my line, these 2 points, instead of being x and y, become cos theta and sine theta. And this is incredibly fundamental to using this unit circle correctly. So what's really important about the unit circle is that the degrees are measured from a different place than what we're used to. Back when we were doing compass bearings, we knew that north was usually up the page, and that was 0 degrees. And that's kind of where we started from. But in this one, instead of being up the page, we're starting from a positive x-axis. So when we're over here, this is our 0 degrees. And this time, instead of working from north down to east, we're going the opposite way. So as I go this way, my number's getting bigger. So over here is 0 degrees, and this up here is 90 degrees. So this is different to our compass bearings, but it's incredibly important that you wrap your head around it. Again, because they're perpendicular lines, the x-axis and the y-axis, each time we move from one to the next, it's going up by 90 degrees. So that first one there is up 90, all the way here is 180 degrees, just like a straight line. Then we move from that into our reflex angles, and if I go all the way down here, this is 270 degrees to that next line. And finally, because it is a circle, it's going to equal up to 360 degrees. So this is going to come all the way back, and that's 360. With this unit circle, it can never actually get out of this position. It's just going to keep going around and around. So if you keep going all the way up from here, you're going to see that instead of becoming something different, it's just going to reset. So this 360 to 540 also falls within this first quadrant. We are going to get into that later if it doesn't make sense, but it's just something to kind of keep your head about. Make sure that you know that the 0 degrees starts from that x-axis on the positive side and works the opposite way to our compass bearings. So we're just going to do a really quick recap of this information and then see how we can apply it to the rest of the circle. So we've got to know that the unit circle sits on top of a Cartesian plane, and the unit circle has a radius of 1. So every point on the circumference is exactly length 1 from the origin. And so because that hypotenuse is 1, or any line from the origin to the circumference is 1, we can find out some incredibly important things about cos theta and sine theta. These actually define how far across and how far up a point on the circumference would be. It's really important to know that cos theta is equal to the x coordinate and sine theta is equal to the y coordinate. So any value that you type into your calculator, say cos 150, cos 200, whatever, the answer is always going to be in between -1 and 1, because our unit circle has that radius. It can't go any further than that. So whatever you type in your calculator is going to fall within those parameters. We're going to see that we can guess quite accurately what that's going to be in this lesson and the next one. So it's our job to determine what the x and y coordinate are, just using an angle of interest. And we can use this incredibly easily without actually having to use a triangle. As long as we've got this idea of cos theta is equal to the x coordinate and sine theta is equal to the y coordinate, we've already done most of the hard work. So it's all well and good in that first quadrant because x is positive and y is positive, so everything kind of works out there incredibly easily. What we've got to look at is what happens if I've got a point over here. It still has to be defined as some coordinate, x, y, but we can work out some incredibly important information relating to our angles of interest with their trig function based on the position of this coordinate. If you're in year 7 and I asked you to find this coordinate, you could do it pretty easily. The first thing you would do is you would tell me, hey, x is definitely negative. It's from 0 going towards the negative side, and y is definitely positive. Because we know that x is cos theta, we can say that in this quadrant, cos theta is negative over here. And because we know that sine theta is y, and y is positive in this quadrant, sine theta has to be equal to a positive number as well. And this pattern holds up all the way across. So if I'm down in this quadrant over here, I know that x has to be a negative number and y has to be a negative number. So if I have cos of an angle that's greater than 180 and lower than 270, so anywhere in this quadrant, I know that cos theta is going to be equal to a negative number. And sine theta is also going to be equal to a negative number. In that last quadrant, we've got one positive one. And again, we can see that that's going to be our cos because our x over here is positive, but the y is negative. And because now we know what the opposite and adjacent sides are, they are cos theta and sine theta, we can work out what tan theta is equal to as well. Because we know tan is opposite over adjacent and we have an angle of interest, we can say that tan theta is equal to the opposite side, which is sine theta, divided by the adjacent side, which is cos theta. So tan is a ratio still based on the position of the y coordinate, or sine theta, divided by cos theta, or the position of the x coordinate. This is going to be incredibly helpful for some of the questions we're going to get in an exam style condition. So something that we're going to have to be able to do is take an angle and determine whether or not the x and y coordinate is going to be positive or negative. It's actually pretty easy, and we're going to see with these 4 points around the unit circle. This first point in quadrant 1, xy, must have a positive x and a positive y. But this means that cos theta and sine theta also have to be positive. So the rule for this is that if the angle that is given is between 0 and 90, or from here to here, cos theta and sine theta are both positive. So we've got two positive ones over here. If I've got a second point over here, the angle now becomes, instead of 90, it's an obtuse angle. So it's greater than 90 and less than 180. In this example here, cos theta and sine theta have to be equal to not both positive, but the y coordinate is positive, or sine theta is positive, and cos has to be negative. It's gone backwards. So cos theta of any angle that's greater than 90 and less than 180 is going to be a negative number. Any reflex angle down here, all the way down here, we're going to have two negative numbers. So cos theta and sine theta here are both negative, and we can see that just by using Year 7 Cartesian plane knowledge. Finally, this one over here, we've got a positive cos value because x is positive, but a negative sine value because the y coordinate is going down. And for this reason, in this first quadrant, because tan is then a positive divided by a positive, tan is positive in this quadrant up here. Where there's one negative and one positive, tan's always going to be negative because they are divided. So tan is negative in these two quadrants. And then in that third quadrant, between 180 and 270 degrees, tan's actually going to be positive because cos is negative and sine is negative. Dividing two negatives makes it positive, so tan is positive down here. So there is an acronym for this, and it is quite helpful, but I would highly recommend knowing why these things are true instead of just remembering the acronym, because you might kind of miss some of the key information. So this first quadrant we say is A because all the trig functions are positive between 0 and 90 degrees. Over in this one, the only one that's positive is sine, so we call this S. That third quadrant there, where tan is positive because the other two are negative, we call T. And that fourth quadrant, cos is positive, so we call it C. So some people use the acronym all stations to central in order to remember this. It is something that could help you out, but making sure we know why something would be negative or positive is the important skill for us to master. So the questions you might get asked is, tell me whether or not this ratio is going to be positive or negative. And we just have to be able to use our unit circle in order to work this out. If you're using that ASTC method, I would chuck that on your thing straight away. We've got all stations to central. But it is important that we can just see kind of what would happen. If you can use a Cartesian plane from Year 7, you can do this. So we just need to know, will sine 140 be positive or negative? So 140 is over here. Y in that situation is up, so sine must be positive. And that's all we have to do. If it falls in that quadrant, you can see straight away that S is there. So that means sine is positive. Or you can remember that anything from 0 to 180 is going to be positive sine value because it's up on the Cartesian plane. When I've got cos 216, 216 is all the way down here. Cos is negative in that quadrant because x is going to the negative direction, so it's got to be negative here. Tan 187, I've got a negative sine value and a negative cos value, so tan must be positive. Sine 300 is over in that last quadrant where its cos is positive and sine is below the y-axis. So that means that sine 300 is going to be negative. Cos 312 is over here as well, and that is a positive number because it's all the way over here. This last one, tan 380, is a bit confusing. A circle's only got 360 degrees, but after 360, it resets. So 360 becomes the new 0, and then it goes up again. Kind of like how when you read a clock, when it goes past 12, it just restarts. So 380 is around once, 360, and then the last 20 goes up to here. So tan 380 in that first quadrant A where everything is positive, tan 380 must be positive. You can actually check all these answers by just typing them into your calculator and confirming for yourself that what I've put down is correct. I know that there's been heaps of information in this lesson and it is going to be a little bit hard for us to get off the ground, but once you've nailed these key fundamental ideas, I guarantee you're going to find trig pretty cruisy moving forward. It's just really the jump from, hey, we're talking about right angles, to what's this circle doing? But if you can get that leap down, I guarantee we're going to be all right. I do hope you found this helpful, and I'll see you later.